Hello students, welcome back to the classroom point. In our today's class, we shall discuss one of the most important topic, resonance, and its a definition, along with the why the molecules are exhibiting the resonating structures and how to write down the resonating structures along with the resonance energy also. So let's begin the class now. The delocalization of electrons. In a molecule through conjugation is called resonance. So here, if you take any particular molecule, there shall be two types of electrons, localized electrons and delocalized electrons. Localized electrons, they don't move from their places, they stick to their place only. But in the case of the delocalized electrons, they move from one place to the another place. Such type of electrons are called as the delocalized electrons. And to show the delocalization, the molecule must have the conjugation. So let us try to see what is the meaning of the conjugation and conjugated systems. Conjugation. So any molecule is said to be in conjugation if a multiple bond is separated by a single bond with another multiple bond. That means it may be triple bond or double bond, positive charge or negative charge, or lone pair of electrons or single electrons. I have taken this system CH2 not required, only C double bond C you can take or C triple bond C also. So any multiple bond is separated with another multiple bonds, that means double or triple bond, or a positive charge, negative charge, lone pair of electrons or single electron with a single bond. So there must be a gap between these two. There must be a single bond between this multiple bond and these systems. So such type of the systems are said to be in the conjugation. So let us take an example here. If you take this molecule, this molecule is said to be in the conjugation because these two double bonds separate by single bond. Let us take another molecule. Here double bond, triple bond separated by the single bond. Hence this molecule also is said to be in the conjugation. And triple, let us see the another molecule. Here positive charge, double bond separated by the single bond. Hence this molecule also is said to be in the conjugation. And in this case, negative charge, double bond separated by the single bond. Hence this molecule also is in the conjugation. In this case, double bond and any one of the lone pair of electron separated by the single bond. Hence this molecule also is said to be in the conjugation. And here single electron, double bond, that means multiple bond separated by single bond. Again the molecule is said to be in the conjugation. So if any molecule is having the same systems or similar systems are said to be in the conjugation. So when the molecule is in the conjugation, there is a chance for the movement of the electrons. So which electrons move in these cases? Sigma electrons never move in the conjugation, only loosely bonded electrons. Loosely bonded electrons meaning here is either pi electrons and negative charge. Negative charge meaning is a pair of electrons. So lone pair of electrons or single electron or charge also. So these loosely bound electrons and charges move from one place to the another place. Hence the system is said to be in the conjugation. So when conjugation system is there, then automatically movement of electrons takes places. Because of the movement of electrons, we get the different structures. Those structures are called as the resonating structures or canonical structures. Now let us see another example here. If you take this particular molecule, this is called as the non-conjugated system. Reason here is, see, both of these multiple bonds separate by the more than one single bond. So here conjugation is not possible. Only in these cases conjugation is possible. When conjugation is there, automatically delocalization of electrons takes place, which produce the various similar structures. Various similar structures are called the resonating structures or canonical structures. All the canonical structures are having the either same or nearly same energy. It is not compulsory for the resonating structures to have the same energy all the cases. It depends on the type of resonating structure they exhibit, that we shall see in the coming discussion. So now let us try to see how to write down the resonating structures. Rules to write the resonating structures. So while writing the resonating structures, the position of the atoms don't move. Here, the position of atoms do not change. Then whose position changes? Only electron position changes. The bonding and non-bonding electrons count remains same. The total charge on all resonating structures remains same. Resonating structures shall have either same or nearly same energy. See, these are some characteristics and rules while writing the resonating structures. Never try to move the position of the atoms. If position of atom changes, means that is not the resonating structure. Only electron's position changes from one place to the another place. Whenever the electron position changes, automatically Lewis dot structure also changes. That means resonating structures are having the different Lewis dot structures. Then whether the resonating structures are having the same energy or different energy. Most of the resonating structures are having the nearly same energy. In some cases they will have the exactly the equal energy. And if there is a charge in any of the resonating structures, the charge remains same. If only one positive charge is there, all cases they will have the only one positive charge. That depending on the how the electrons are moving from one place to the another place. So by applying these rules, let us try to learn the how to write down the resonating structures. First one is move pi electrons towards pi bond. That means in any of these structures, if two pi bonds are in the conjugation, then move the pi bond from one place to the another place towards another pi bond. So we shall take an example here. CH2 double bond CH, CH double bond CH2. So these two double bonds are in the conjugation. Then in such cases, move the one pi bond towards the another pi bond to get the resonating structure. So here CH2, since this double bond, one of the bond shift that side, here we get the single bond. Next here double bond comes, here single bond, CH2. Look at this side, these pi electrons are completely shifted to this carbon. Hence this carbon gets negative charge. These pi electrons are leaving this carbon. Hence this carbon will get the positive charge. So now these two are the resonating structures. Moving of the pi electrons from one place to the another place towards another pi bond. Let us take another example. Benzene molecule. Now you can move this pi bond towards this pi bond towards this pi bond, and this pi bond towards that pi bond, so that we get the one more structure. Here pi bond comes, here pi bond, and here pi bond. This is the first structure, this is the second structure. Now again these electrons try to move from this place to this place, giving the structure. So the various structures that are developed during the conjugation or delocalization of the electrons are called the resonating structures, or simply can be called the canonical structures. The energy of these canonical structures may or may not be same. See, in this case, the energy of the canonical structures is not exactly same because they are not identical. They do not look identical. But in this case, both of these resonating structures looks identical. Hence, in this case, resonance, whatever the energy is there with this associated with these structures, shall remains same. That's why resonance structures may or may not have the exactly same energy. Then, whatever the arrow mark we are showing here, this arrow mark says that these are readily interconvertible structures. That means one structure can easily convert into the another structure. And it never says about the position of the equilibrium. So there is no equilibrium between any two resonating structures. That means it is clearly saying that these resonating structures do not have the real existence. That means we cannot isolate these structures. So the molecule we cannot expect that the molecule is staying fraction of time in one structure and the another fraction of time in the another structure. So molecules don't exist like that. And one more information is these resonating structures do not have the real existence. Then the actual structure is the intermediate of these structures. Now look at this side. Sometimes double bond is here, sometimes double bond is here. So in this structure double bond is here, in this structure double bond is here. That means basically the skeletal structure remains same like that. Only pi electrons are moving from one place to the another place. That's why we can show the moving electrons. That means delocalized electrons like this. So this can be shown like this also. That ring represents the delocalized electron, that to 6 pi electrons in this case. So this is the intermediate structure of both of these canonical forms, which is called the resonance hybrid. So resonance hybrid represents the most of the chemical properties, and canonical structures or resonance structures don't explain all the chemical properties of the molecule. For example, if you take the benzene, so some of the properties of the benzene is explained by this structure and some of the properties are explained by this structure. But all the properties are explained by the intermediate structure, that is the real structure, which is the resonance hybrid. And in this case, how to write down the resonance hybrid? So writing of resonance hybrid is CH2 single bond remains here. All the single bonds don't change. Then what changes is pi electrons. Sometimes pi electrons are here, sometimes pi electrons are here, and sometimes pi electrons are here. In that structure, pi electrons are in these two places, and in this structure, pi electrons are here. That means the electrons are moving from one place to the another place. That gives these bonds partial double bond character. That means single bond is always confirm, pi bond is not confirm because it is not this stable bond, it is the delocalized bond. But the charges developed here is partial negative charge is here and partial positive charge is developed there. We can take one more molecule. So like this. Move pi electrons like this, we get the one more resonating structure. So move pi electrons from this place to this place. So electrons shift there. These pi electrons move this side. So like this, we can move the pi electrons from one place to the another place towards another pi bond and getting the various resonating structures. Next one is move pi bond electrons towards positive charge. Example, let us take allyl cation. So in this allyl cation, these pi electrons and positive charge separated by the single bond. That means it is in the conjugation. So that you try to move these pi electrons towards the positive charge. So we get CH2, CH double bond CH2. See, because these electrons are coming here, this positive charge, these electrons get neutralized. Since electrons are leaving this carbon, positive charge is developed on this carbon and we get one more resonating structure. So its resonance hybrid can be written as, see, the electrons are moving from this place to this place and developing the positive charge on both of these carbon atoms. In one structure here and another structure this side carbon. So let us take the benzyl cation. Move the pi electrons towards the positive charge. So that electrons comes here. Positive charge developed on this carbon. Next, these pi electrons move towards this side. Positive charge comes here. Next time positive charge, pi electrons moving this side. Positive charge comes here, and in the next structure these pi electrons, because every time they are in the conjugation. So altogether we got the 5 resonating structures for the benzyl cation, and its resonance hybrid can be shown as, see, these electrons are keep on moving throughout the structure. Here on single bond, CH2, pi bond also sometimes present here. And positive charge is developed on this carbon, and next this carbon, next this carbon, and this one. So that here wherever the positive charge is developed, there you can place the partial positive charge, delta positive charge. This is the resonance hybrid of all these 5 resonating structures. Let us take the tropylium cation. Now you can move either this pi bond towards this side or this pi bond towards this side. Let's move this pi bond towards this side, towards the positive charge. So pi bond comes here, this here one pi bond, here one pi bond, positive charge is developed here. Next this pi bond changes. Next this pi bond moves here. Next again this pi bond moves here. Next this pi bond moves here. Next this pi bond moves here. Finally this pi bond moves there. Giving the resonance structures. See, the similar structure is developed. Till the similar structure is developed, we have to keep on writing the resonating structures. So in this case, the first one and the last one are identical, same structures. And number of resonating structures, 1, 2, 3, 4, 5, 6, 7 resonating structures are there. And its resonance hybrid can be written as this is a skeletal structure. And pi electrons are moving everywhere and positive charge also developed everywhere. See here, this is, if you imagine this is the first carbon, here third carbon, here fifth carbon, here seventh carbon, and here second carbon, fourth carbon, sixth carbon, again first carbon. That means every carbon atom the positive charge has been developed. Hence we can show the delocalized electrons like this. And every carbon is developing the positive charge so that you can show the positive charge in the center of the ionic molecule. So like this we can write down. Let us see the other category also. Move lone pair of electrons towards pi bond. So in this case, pi bond and lone pair of electrons are in the conjugation, so that you move the lone pair towards the pi bond. So example, CH2CHCl. This is called as the vinyl chloride. So now this lone pair of electrons and pi bond are in the conjugation. Always moves lone pair of electrons towards the pi bond so that pi electrons shifts to the next atom. Two resonating structures. Let us write down the phenol resonating structures. So this lone pair of electrons moves here and this electron shifts here. So you must observe clearly where the electrons are being shifted. Lone pair of electrons are shifted between the oxygen and carbon. So that here we are showing the point exactly between both of these. And these pi electrons are not shifting here. They are shifting to the corner. That means atom. So that's why you must be careful while writing the resonating structures. Here double bond OH. Since oxygen is losing electrons, it gets the positive charge. And this pi electron shifted here so that it gets the negative charge. Next, negative charge. Again move this negative charge. Now move this negative charge, electrons are shifted to the oxygen back. So like this we can write down the resonating structures for the molecules in which lone pair of electrons and pi bonds are separated by the single bond. I will give one work. Try to write down the resonating structures for both of these molecules. This is aniline. So write down the resonating structures by shifting the lone pair of electrons and shifting these pi electrons to this corner. And anisole. So this is called as the methoxybenzene. So here also shift one of the pi electrons. Here also two lone pair of electrons are there, but we are shifting only one lone pair of electrons. So only one lone pair of electrons participate in the shifting process. Here also shift only one lone pair of electrons and this pi bond to this corner, and remaining structures look similar. And since here nitrogen is losing electrons, nitrogen will get the double bond here and positive charge. Oxygen, this lone pair of electrons after shifting here, it will get the double bond and here positive charge. So using this clue, you write down the resonating structures for both of these molecules. Now let us see the remaining part. Negative charge towards pi bond. So when pi bond and negative charge are separated by the single bond, then try to move the negative charge towards the pi bond, but not the pi bond towards the negative charge. Let us take some examples here. So I am taking the allyl carbanion. So negative charge, double bond separated by the single bond, they are in the conjugation. Shift, move the negative charge towards the pi bond. So we get the another resonating structure. This is benzyl carbanion. So move the negative charge towards the pi bond. Negative charge developed here. And by shifting the negative charge towards the pi bond, we get one more resonating structure. And by shifting like this, the other resonating structure. And finally, we are getting this resonating structure. So again, here also 5 resonating structures are there. Now you write down the resonating structures for this particular molecule. Phenoxidone. By shifting the negative charge, and here this will shift over here. So similar resonating structures we shall get here. Move pi bond towards odd electron. Odd electron means single electron if it is present. So example, allyl free radical. So in this case, already one particular electron is present here. It doesn't need a complete pair of electrons. Only one more electron is enough to develop the bond here. That's why this pi bond undergoes homolytic cleavage and giving only one electron on the other side. So we get here CH2 radical here, and from this bond one electron and here one electron. Both together develops the bond, getting the another resonating structure. So now you write down the resonating structures for this particular molecule. Benzyl free radical. Using the similar concept, break this bond into two homolytic cleavage so that one radical comes here and bond comes here. This electron and half electron from this bond develops the bond over there. So write down the various resonating structures for this benzyl radical on your own. Move lone pair of electrons towards positive charge. Here positive charge is present, oxygen, methyl group, see lone pair of electrons. So whenever positive charge lone pair of electrons separated by the single bond, move the lone pair of electrons towards the positive charge because positive charge attracts the electrons. So it gives another resonating structure where oxygen gets the positive charge. So these lone pair of electrons move towards the positive charge, giving the resonating structure. So this is the way to write down the resonating structures. Now let us try to learn which resonating structure is more stable among the various resonating structures of a molecule. Stability of resonance structures. So the first one is more the number of bonds, more the stability. So whichever resonating structure is having the more the bonds than the charges, that is more stable. Why? Because the formation of the bond always loses the energy. So more the energy lost, more will be the stability of the molecule. That means neutral molecules are more stable than the ionic species. So here we can write down that neutral molecule is more stable than its ionic form. So let us take an example here. But 1,3 diene. So when the electrons are shifted here, we get another resonating structure, structure 1 and structure 2. So between these two, this is having more number of bonds, because in that case, one of the bond is converted into the charges. So wherever more number of bonds are there, that is more stable. So here this particular first structure is more stable. Next one, atoms with octet electronic configuration. Are more stable. So whichever the atom is having in whichever structure, all the atoms are having the octet electronic configuration, such structures are more stable. So let us take an example here. So in this particular example, this particular carbocation CH2 plus is having 6 electrons. So by shifting this pair of electrons between these two atoms, positive charge and lone pair of electrons. In this particular case, every atom is having the octet electronic configuration. So octet configuration is possible in this case. Hence, this structure is more stable than the previous structure. So between these two, that structure is more stable. Let us take the second example. Here, this CH2 plus is having the 6 electrons. So this shift the other side. Octet electronic configuration. And this is stable structure. And third one is separation of charges needs energy. Hence, more the distance between the charges, that means opposite charges, less the stability. So let us try to take the molecule CH2, 1,3-butadiene I am taking here. Shift these electrons. Next, shift these electrons. So now we got the 3 resonating structures, structure 1, structure 2 and structure 3. So among these resonating structures, this is a neutral molecule. As according to our first rule, neutral molecule is always more stable. So first one is more stable than the remaining 2 structures. In the remaining 2 structures, here opposite charges are nearby and their opposite charges distance increase. So where if you want to send both charges to the longer distances, you need more energy. So more energy means the molecule is having the higher energy. Higher the energy means less the stability. That's why less the distance, more the stable. More the distance, less the stable. So second structure is more stable than the third structure. Next, fourth rule is presence of negative charge on more electronegative atom stabilizes the structure. So let us take a molecule here. In this structure, negative charge is on the carbon. Carbon is a less electronegative atom. So it participates in the conjugation. Now, negative charge is on the oxygen. Oxygen is a more electronegative atom. Hence, this structure is more stable. Next, presence of identical charges on adjacent atoms destabilize the structure. So if you take any particular molecule, in that if identical charges are present, see both negative charges or both positive charges present on the adjacent atoms, that structure is least stable. So to understand the stability of the resonating structures, the rules must be followed is always try to check more the number of bonds are there or not. If more the number of bonds, more will be the stability of the structure. After that, you need to check the octet electronic configuration with every atom. So if the structure with octet electronic configuration for every atom is more stable. After that, we need to check the presence of the negative charge, whether it is on the more electronegative atom or less electronegative atom. If it is on the more electronegative atom, more stable. If it is on the less electronegative atom, it is less stable. And the last one is choosing the identical charges on the adjacent atoms. Now let us try to check one particular example and let us try to write down the stability of the various resonating structures. So these structures, let us try to put the charges also. So if you observe, if you try to develop the decreasing order of the stability of various resonating structures, we must check the number of bonds first. Because all these resonating structures are having the same amount of the charge, plus minus, plus minus, minus plus, minus plus. So one positive charge, one negative charge is present. So if you count the total number of bonds here, so number of bonds, two plus 2, 4 and 2 with hydrogen, totally 6 bonds are there. Here 2, 1, 3, 3 plus 2 bonds with hydrogen, 5 bonds are there. 3 plus 1, 4 plus 2, 6 bonds are there. 2 plus 1, 3 plus 2, 5 bonds are there. So among all these resonating structures, structure 1 and structure 3 are having the more number of bonds. That's why structure 1, structure 3 are more stable than the remaining 2 structures. Now the question is, between structure 1 and structure 3, which is again more stable. So if you observe that in structure 1, negative charge is on the more electronegative nitrogen. In this case, negative charge is on the less electronegative carbon. Hence, structure 1 is more stable than structure 3. Then if you consider both the second structure and fifth structure, fourth structure, both are having the same number of 5 bonds. But in the second structure, negative charge on the more electronegative atom, and in this case, negative charge on the less electronegative atom. So that's why second structure is more stable than the fourth structure. Hence, we can write down the 2 is more stable than fourth structure. So this is the way we can identify which structure is more stable among the given resonating structures. Now let us write down the one more here. Resonating structures of chlorobenzene. So among the 5 resonating structures, 1, 2, 3, 4, and 5. The order of stability is, see, first structure and last structure, fifth structure, both are having the more number of bonds, no charge is present, and they are identical almost. So 1 is equals to structure 5. And if you see the second structure and fourth structure, charge distance is same. But in the case of the third structure, distance between the opposite charges is more. That's why second structure is equally stable as the fourth structure and more stable than the third structure. So this is the order of stability of the resonating structures of the chlorobenzene. Now let us try to see what is the resonance energy. Resonance energy. The definition of resonance energy is the difference in energy between the calculated and experimental heat of hydrogenation is called resonance energy. So let us try to see what is the meaning of the heat of hydrogenation. Heat of hydrogenation is nothing but during the addition of hydrogen molecule to the unsaturated systems, it liberates some amount of energy. That energy is called the heat of hydrogenation. Let us take the cyclohexane molecule. Cyclohexane molecule, when hydrogenated, when added with hydrogen, it gives the cyclohexane molecule. Its heat of hydrogenation is minus 28.6 kilocalorie per mole. This is the experimental value. And if you take the benzene, see here, for one pi bond, the molecule is releasing this much amount of energy. Here 3 pi bonds are there, so that if 3 molecules of H2 is added to get the cyclohexane molecule, the heat of hydrogenation is 3 times of this. That means 85.8 kilocalorie per mole. This is calculated value. But in original, when benzene is hydrogenated, that much amount of energy is not released to convert it into the cyclohexane molecule. So the experimental value is minus 49.8 kilocalorie per mole. So this is the experimental value. So in the case of benzene, calculate, that means expect amount of energy this much, but actually release is this much. So the difference in energy between both of these is 36 kilocalorie per mole, or approximately 152 kilojoules per mole. So the difference in energy between the calculated heat of hydrogenation and experimental heat of hydrogenation is called the resonance energy. That means expected this much amount has to be released, but actually released is this much. That means the molecule is stabilized by this much amount of the energy. So the molecule is possessing this much less energy. So lower the energy means more the stability. That's why we can say that when resonance energy increases means gap increases. Gap increases means the molecule is going even to the lower energy states. So when the resonance energy increases, stability of the molecule also increases. There is one more definition for the resonance energy. That is, if you take a different resonating structures of a molecule, so take different resonating structures. Imagine this is the first resonating structure, this is the third resonating structure, this is the second resonating structure. So second is the lowest energy state among the resonating structures, and take the resonance hybrid. So the energy gap between the most stable resonating structure or canonical form and resonance hybrid, that energy gap is called as the resonance energy. So more the resonance energy, more will be the stability of the molecule. Then let us try to see whether all the molecules, all the resonating structures are having the same resonance energy or not. So resonating structures may or may not have the same amount of the energy. The reason is, if the molecule is having the equivalent resonating structures, in that cases, all the resonating forms, that means all the canonical forms will have the same energy. But if the molecule is having the unequal resonating structures, then the energy of the resonating structures is not same. Let us see which molecules are exhibiting the identical resonating structures. The molecules or ions with equivalent, that means identical, resonating structures. So you must remember one thing, that more the number of resonating structures, more will be the stability of the molecule. Reason is, when the number of resonating structures increases, the delocalization of the electrons or the charges also increase. More the delocalization of the charge, so the charge is not stable in a particular atom, so that it is not available for the attacking reagent. It always moves from one place to another place, which gives the stability to the molecule. So that more the number of resonating structures, more will be the stability. But in case of the equivalent resonating structures, if any particular molecule or ion is having the equivalent resonating structures, even though it is having the lower number of resonating structures, but equivalent resonating structures gives the more stability to the molecule or ion than the molecule with the more number of resonating structures. So when you are comparing the two molecules, one is with equivalent resonating structures but less number of resonating structures, another one is having the more number of resonating structures but unequal number of the resonating structures. In such cases, the first case is more stable because of the equivalent or identical resonating structures. Let us see examples. The first one is allyl cation. Its both resonating structures looks similar. So these are called as the identical resonating structures, both. Next one is allyl carbene ion. Here also both of these resonating structures looks similar. Allyl free radical. Identical resonating structures. Take the benzene molecule. Identical resonating structures. Take the carboxylate ion. Identical resonating structures. Take the ozone molecule. It has the identical resonating structures, means both looks the same. Take the carbonate ion. So one time double bond you place here, one time here, other time here. So these are all identical resonating structures. So these are all more stable ionic species or the more stable molecules because they are all having the identical resonating structures. One more is there, that is anilinium ion. Again, identical resonating structures. So these molecules are having the identical structures but less number of structures, but these are more stable than the other molecules which are having the more number of resonating structures. Now, let us try to see why the molecules are exhibiting the resonance. So, we have already seen that various molecules and writing of the resonating structures, but the question is always about why the molecules are exhibiting the resonating structures. It is important to recollect the information from the Lewis dot structure, that using the Lewis dot structure, we are developing the structure to a structure for a particular molecule. But while drawing the structure, it is not compulsory to keep the lone pair of electrons or bond pair of electrons between the only one type of atoms, and you can write down the similar structure with the same number of electrons. In such cases, you may get the more than one type of the Lewis dot structure. So, if one Lewis dot structure is not able to explain all the chemical properties of the molecule, then there is a chance to develop the one more Lewis dot structure for the same molecule. But remember that using all these resonating structures, no canonical form explains all the chemical properties of the molecule. Let us take an example of the ozone. So, in ozone molecule, we can draw the structure of the ozone molecule like this, or we can write down the Lewis dot structure for the ozone molecule like this also. So, either of this or that structure explains all the chemical properties of the ozone. None of these both structures explain all the chemical properties. Very interesting thing here is, if you observe this bond length between the two oxygen atoms is 121 picometers, and this single bond length is 148 picometers. There also it is similar. Here 148 picometers, here it is 121 picometers. But experimentally it was found that the bond length is not either 148 picometers or 121 picometers. The bond length between both of the oxygens, means by seeing these two structures we can expect that ozone is having the two type of the bond lengths. But experimental observations reveals that ozone is not having the two different bond lengths. It is having the only one type of the bond length, that is 128 picometers. So 128 picometers means it is more than the double bond length and less than the single bond length. That means it is having the partial double bond character like this. So this is called the resonance hybrid of both of these structures. So resonance hybrid explains all the chemical properties of the molecule. So dear students, I hope you understand this video and this video is informative. If you really understand, please do like my videos and share with your friends. Thank you one and all.